Assalamu alaikum. Today's lecture is about design of welded joint, and this is chapter 9 of machine design book. We will be studying from introduction of weld. In workshop technology, you have already studied what is welding and different types of welding, and I hope that you have also performed welding process. By This chapter starts with the definition of welding. Welding is the joining process in which two or more parts are coalesced at their contacting surface by application of heat or pressure or both of them. In some of the welding process, we add filler material, and the other we don't add filler material. And how we differentiate between this process, I will just explain it. I will explain it in next slide. This is one picture of welded joint. There are two type of welding process. One is fusion welding, and the second one is solid state welding. Fusion welding is the welding which you usually see in electric car in shape of electric arc or gas welding. In these welding types, usually we melt the base metal and we add filler material which mix with the base metal, and then after solidification it makes a bead on the weld. This is a filler fusion welding in which we add filler metal as well. The second type is solid state welding, in which we do not melt the base metal. Sometimes we need to add heat as well. So we join metal either with only pressure or a combination of heat and pressure. Even when the heat is applied, it is usually below the melting point because we do not melt the metals. And as the metals are not melted, there is no need to add any filler metal in the solid state welding. Like any other process, we have some advantages or disadvantages of welding process, and here we are comparing welding process with other fastening method, which are either fasteners, nuts, nut bolt, or rivets. The main advantage is it is a permanent joint. It is usually stronger than material. Welded joints are usually stronger. It is more economical way to join. Just imagine you are welding 1 meter of weld, or on the other hand you are adding 10, 20 or 30 nut and bolt. Uh, Welding is economical. Also, it is not restricted to a factory environment. You can you have a portable unit that you can bring anywhere, and you can just start welding. Its efficiency is higher. Its alteration is can be easily made as compared to nut and bolt. For example, if you need to add join two metal two parts, and by nut and bolt you have to have some space to make a hole. Then you have to first initially you have to drill the hole, then you have to put the bolt, and on the other hand you have to have space for rivet nut, and then you should have space for tightening nut and bolt. In case of welding, this is not the case. You can just weld two parts. Also, welding is smooth in appearance. You can The surface is very pleasing. And after welding you can just paint it and it will not be visible, and also it takes less time. On the other hand, we have some has some drawbacks as well. If you have to disassemble the part, then welding is not an option. Then you have to go for nut and bolt. Also, for welding you need very highly skilled labor. It Because of heating and cooling cycle, the the parent metal is passed through a thermal cycle, so stresses are generated. For this process you need to have extra energy. You need utilize energy, and it is also dangerous for the worker as well. And also, if there is any defect within the weld, you cannot see from your naked eye. For that you have to have some expensive material, expensive instrument to check the defect. So this is in that matter it is an expensive process as well. From welding we join two or more parts, and from nuts and bolts or from rivets as well we join one or two parts, two or more parts together. For joining metal we have different type of joint. Basically we have in general five type of joint. One is butt joint, corner joint, lap joint, T joint, and edge joint. Butt joint is the joint which you can see in the figure when two parts are placed on one plane and you just weld the boundary of these two. This is the butt joint. And if you join it by weld, it is butt joint by weld. And if you want to make a joint with the help of nut and bolt, you can just place a plate here, and then you can add two bolt here, two bolts here, similarly a plate on the bottom, and the same butt joint can be made by nut bolt or rivets. Then we can have a corner joint where two parts are placed corner to corner, joined by the corner, and the weld is made here. We can have lap joint. We can weld here and on the other surface, or if we want to make this lap joint by rivets, we can add two or more rivets here, and the same joint can be made either from weld or from rivets. We can have a T joint where we can weld this surface here and on the other side as well. Or this T joint, for this T joint we can just pass screw from here and through this surface and make this T joint with nut and bolt or screws as well. Edge joint, in order to join these two metals, either we can weld it, this will be the welded edge joint, or we can just put bolt from here and it can be tightened from nut on the other side, so the same edge joint can be made from nut, bolt or rivets as well. To make either of the five type of joint, we need to have some types of weld as well. In general, we have four basic type of weld. One is fillet weld, second is groove, plug slot and flange weld. Fillet weld is this when two parts are just placed on one on the other, and the space is filled with the weld, and this extra space means that the filler metal is also added in this part. The filler metal melts, the base metal is melted and the filler metal also melted, so the final bead is the combination of base metal and filler metal. Usually the filler metal is made of almost the same material as the base metal, because strength is not a greater issue as well in case of welds. This can be double edged like this, or this is also double edged. Group weld is carried out in case of butt joint. The main disadvantage as compared to fillet weld is that in terms of group weld, we have to prepare the edges. For example, in this edge butt weld, we have to prepare these edges so that there is no impurity, no particles within the edge. So before welding, we have to prepare these edges. Similarly, if you see that we have prepared these edges, plus we have made a small slot in the right hand side, so that the weld is the in metal is melted from here as well, so the weld is a little bit more stronger than this. Also, we can make is V weld, U groove or J groove, or we can make the groove on both sides of the weld. So these are different types of groove weld. Plug is or slot weld. If the plates are very long, then we it is not feasible to weld it from here or other two sides, because the plates are very long, so there will be a deflection of plates in between. There will be also always be a gap. So to overcome this problem, we make a plug, or we make holes on the upper plate, or we make slot on the upper plate, then we make a weld, and the weld is the whole groove or hole is filled with the filler metal, and the final weld is made. So this is usually for long flat plates. Spot or seam weld, it is not the type of fusion welding. It can be characterized in fusion solid state welding as well, because there is no filler metal added and the part is not melted from the surface. Usually electrode, we have one electrode here, one electrode here, two electrode. The high ampere current passes through the electrodes and force is applied. Due to when the current passes from here, because there is a gap between two parts, the heat is generated, and due to that heat, these two parts, these edges are melted, and due to application of pressure, and when it solidifies, it makes a solid joint, which is very common in mechanical engineering. This is slot spot weld. We made a lot of spots, or it is a seam weld. The same process is carried out when there are two rollers, one on the top and second on the bottom. We also have flange weld. Flange weld, this type of weld is called flange weld. We just completed the introduction of different type of welding process, different type of welds that we have, different types of joint. Then now we have to study how to design a welding process, how many stresses are there in the weld, how to calculate the stresses, and how to calculate maximum force that a joint can support. First of all, this is the welding symbol. If we have a weld here, we just point an arrow towards the weld and then make a straight line, and this straight line has a lot of details on top and bottom, which explains what is it this weld is all about. This arrow points towards the weld. After that, this circle shows that this weld is all around. In coming slide, when we will see the weld, you will just experience what these symbols are about. This L minus L dash P is length of weld, and it is also pitch of weld. When we make a small spot weld, this is the one is length of each spot, and then this is the gap between two spots. Then this is the this both side, this shows what type of weld we are using, and then arrow side, this towards arrow side shows the what is height, and this is on the other side of the arrow. For example, if you have 2D space, if we have this type of surface and arrow is pointing towards this end, then one end shows what is the weld in this side, and the other side shows what is the weld on the other side of arrow. For example, this one, this is the other side of the arrow. And remaining things you will this is number of spots, 10 spots, 20 spots, 30 spots, how many spots we are making. In this picture we had which type of weld we are using, this basic weld symbol, and these are the weld symbols. For example, bead weld, fillet weld, or plug and slot weld, and these are the different types of groove weld. For example, this 5 with this arrow shows there is a fillet weld of height 5 millimeter or inches, and weld is made here. For example, this or this. So for example, this and this, and because this triangle is on both sides, it means that if this arrow is pointing towards this end, it means that on the other side we have same weld. Similarly, if this weld is pointing towards this end, on the other side we have exactly same weld. Similarly, these two welds, we have a weld of 60 mm width, and it is made after 200 mm of distance. At center to center distance between two weld is 200 mm or inches, whatever units you are using. Again, we have 5 fillet weld of 5 millimeter high. This is height, this is height, and this circle shows that this weld is all around. This shape of welt is all around the joint. These two welts means we have this V welt on both sides. For example, arrow is pointed towards here. It means that on the other side as well we have same point weld. Similarly, though two vertical lines, square weld, we have square weld on both sides. This is bevel. We have bevel weld. One surface is flat and the other surface is cut at 45 degrees. So we have bevel joint. 60 degree and 2 means 2 mm of or 2 2 mm of gap between two parts, and then these are both the surfaces are cut so that they make a V. Similarly, we have from this symbol it is not clear, but with this symbol there will always be this figure. So this figure shows that for at this point we have a groove weld. Sorry, fillet weld. Sorry. This show that cut the we have prepared this portion initially, and then we have made a fillet welt, or a bead. We have made a fillet welt here. This is for U type or J type, and this is for square. The weld is square. Both the parts are made, has not prepared, has not cut to any angle. They are made square, and the material is welded. Sometime in the weld we do reinforcement. What is reinforcement? For example, these two metals, part 1 and part 2, are required to be welded. So we weld it here. This is minimum height, which is throat at of height h. Usually we make some bead like this and this portion. This is reinforcement, because at this point cross section area is larger as compared to this. So larger cross section area means less stresses here. But what is the disadvantage? Because at this point we have sharp edge along the length here. On the other side, on the bottom of both sides, we have sharp edges, and due to this sharp edges, local stresses are very high, and there is a possibility of yielding at these points. So in that case we just trim off the extra surface and make this flat surface. And due to flat surface, there is no stress concentration at the sharp edge. As there is no sharp edge, is no stress concentration. For this weld, for this simple butt weld, we need to calculate what are the stresses, normal stresses in the weld. How do we calculate? We have the force, and what is the normal area to this force? Normal area is this height multiplied by this thickness. This, for example, this area is normal area. So F divided by H is height, and L is the length of groove. So F divided by HL is the normal stress in the weld. And so similarly, average stress, if you need to calculate average shear stress, that stress, if the force is acting in this direction and in this direction, so on the same area, which is H by L, and this force divided by that area will give us shear stress on this welded area, this cross section area. I have taken this point because usually we trim off the extra portion on the top and on the bottom. Now we have very simple equation to calculate stresses, but what else we need to calculate? For example, for butt weld it was very easy, but in case of lap weld, we weld fillet, and for fillet, if it is 45-degree angle, this is the shortest possible cross section area of weld. And if you enlarge this picture, this area is the shortest, because if this length is h, this t is, what is this t? If we have 45-degree, we need to calculate this t as a function of h. So we have this angle is for theta, this is 45-degree, and remaining this angle is 180 minus 45 minus theta. So forces in this surface, we have shear force and we have normal force. Normal force is Fn, F cos theta, which is this angle theta, and Fs is F sin theta. So we have shear force and normal force on this area. This area can be at any angle. We have not concluded that it is 45-degree, 30-degree or 60-degree. Initially we have used it as theta, and later on we will calculate what is this theta, where the area is smallest. So using sine law, t by sine 45, h divided by this angle, and h, which give us h divided by 135 minus this angle, and we will get final equation of this final equation in between t and h. So this equation gives us the value of t as a function of h. So we have t is equal to h divided by cos theta plus sine theta. This is the t. And when this theta is equal to 0, when this theta equals to 0, we come here, and here we have theta 0 cos 0 1 plus 0, so t become h. Similarly at 90 degrees, sin theta is 1 and at 90 cos theta is 0, sin theta is 1, so again t is equal to h. So we have this very well written the equation. Now we have t. What is the average normal stress at theta? For example, this theta, what is the average normal? This is force divided by area. What is the area? T multiplied by length, which is in this case in to out of the paper or in the towards the screen. So we have the equation of t in terms of h. We substitute this equation in this equation of sigma, so we will get final equation of sigma of normal stress. This is the normal stress in this cross section. Similarly, for shear stress, tau is equal to Fs TL if the force is acting in this direction in the paper or out of paper, then so that will be other case. Now for this force we have one shear component, and that shear component is applying some shear stress here, and to calculate that shear stress we have this equation. We substitute t equal to h divided by sine theta cos theta, and we will get final equation of tau. We have equation of normal stress, and we have the equation of shear stress on lap weld. These are the two sigma and tau we have calculated for lap joint. What will be the maximum shear, and where will be the maximum shear? For that, we uh, why maximum shear? Because usually weld fail due to shear, not due to axial loading or not due to normal stress. So we differentiate d tau divided by d theta, we calculate this, and with reference to theta we calculate the value of tau, the angle theta for which value of tau is maximum. So we differentiate d tau by theta equated to 0, and we will get the value of theta equal to 67.5. So at 67.5 degree angle, the shear stress is maximum. What is the amount of shear stress? We substitute this theta in this equation and also in this equation, so we'll get final equation of tau is equal to 1.207 f divided by HL, and similarly sigma is equal to 0.5 of this stress. So this is the maximum shear stress. On the other hand, if we want, we can also calculate von Mises stress. What is von Mises stress? You have not studied von Mises stresses yet, but in MOM 2 you will study von Mises stresses. It is a unique stress property, scalar quantity, which show the maximum magnitude of stress, a combination of stress. Usually we have combination of normal stress and shear stress at a point. Von Mises stresses gives us a unique scalar quantity equivalent stress at that point. For this is the you can see the equation of machine design book, this for 514 for 3D space and 515 for plane stresses. I have taken this equation, 515 equation for in case of plane stresses. Plane stresses or 2D stresses, simply stresses in a plane. In case of weld, we have only one stress, sigma x. We don't have any other stress. So this equation will be further simplified to sigma square plus 3 tau square. So this term sigma y is 0 and sigma y is 0. So this equation will further be simplified. Von Mises stress will further be simplified as a combination of normal and shear stress. So substituting these values of normal and shear stress is here. So we'll get this equation in terms of theta. And what they have done, maximum, they have calculated a value of theta where von Mises stress is maximum. So differentiating this sigma prime with respect to theta and equating it to 0 gives us theta equal to 62.5 degrees. So at angle of 62, theta is equal to 62.5 degree, von Mises stress on the fillet weld is maximum or lap weld is maximum. So substituting these values in sigma and tau will give us at 62.5 degree, sigma maximum is 2.16 and tau maximum is 1.19. Here tau was 1.20 because it was the maximum value of tau in the weld, but this is a little bit less. But as this equation is a combination of shear and normal, so the overall resultant is maximum in this case. But I have already told you that weld will always fail due to shear, not due to axial loading. So we will be preferring this value or this value. How to judge? For this, or sorry, also I have calculated value of 6.23 because at this point 1.1 is tau, but sigma is higher as compared to this one. So overall magnitude or overall representation of stress is higher. Uh, so either we use this value theta 67.5 or theta 62.5. For this we have to see what other people have done, because there is no direct relationship between actual representation, actual behavior of material and mathematical models. So we go to the actual data, experimental data by some researchers. So Norris in 1945 calculated the distribution of stresses between A to B and B to C, A to B and B to C on the boundary. And these equations are valid for weld plus base metal, both the material, the black material or and pink material as well. But it did not study what is the stress distribution within the bead from D to B, or within a black region what is the stress distribution. In 1937, Selekian studies the stress distribution between B and D, between this line, and they showed that stresses are higher at B as compared to D. So if we have to save the weld, we can just study the stresses at point B. If here as well, if you see that stresses are at B are higher in complete weld, the point B is most dangerous points. Similarly, here point B is the most dangerous point. So from that data, we can just predict that point B is a little bit dangerous. But how much? Because we don't have, after these 70-80 years, still we don't have any direct relationship between stress and stresses applied on weld. So, and yet we don't have any equation, yet we have to make our weld that is safe and reliable. And what we do for that, we make a conservative model. This term conservative you will listen again and again. What is conservative? Conservative is, for example, if you know that from going from Rawalpindi to Lahore and staying there for 3 to 4 days, you need 5,000 rupees or 10,000. Say 10,000 rupees for 4 to 5 days. So if you are conservative, you will just say that I will bring a little bit extra, 11,000, 12,000, 13,000, not 1 lakh. So that is a little bit conservative. You take a little bit extra. Or if you don't or just study like this, if you are coming to class and you say that from reaching from hostel to class is 10 minutes, and getting ready is 10 minutes extra, doing breakfast is 10 minutes extra. So you say that in total from waking up to reaching to class you need 30 minutes. So being conservative, you add 2 minutes extra to each activity, and you say that 2 minutes extra to waking up, 2 minutes extra to preparing, and 2 minutes extra going to class. So a total of 36, you need a total of 36 minutes. So that 6 minutes are little bit extra. You took a factor of safety. So this is a term conservative. So what is a conservative model? It is simple model. You have studied what are the stresses acting upon if you take maximum shear stress, or if you take a maximum amount of von Mises stress. In conservative model, they use exactly same equation, this equation, von Mises equation, and in this equation they excluded the effect of normal stress, and they just consider the complete effect of shear stress. So shear stresses, due to shear stresses, von Mises is maximum at some other section, and then they differentiated again this value von Mises stress. They differentiated this value d sigma prime by d theta, then equated it to 0, and then calculated, they got a value of theta equal to 45 degree. And they said that this angle at this, if they take cross section area at 45 degree, they get a maximum shear stress. How much maximum? When they substituted this value in the equation, they got a value of 1.414. And if for maximum stress, what was the maximum shear that they got initially? That was 1.207. So this value 1.414 is 17% more than the maximum stress. So they have taken a factor of safety of 1.17 already. So from now on, we will be just using a maximum value of 1.414, which is sine of or cos of 45 degree here. This is divided by cos of 45 degree or 1.414. So it is also easy to remember, f divided by hl sine 45 degree. It is 1.411 is also simply here sine of 45 degree. So factor of safety is 1.17 or 17% extra. So the our model is more conservative than the maximum shear stress model. So the what was the change? In this change, the entire force is accounted by the shear stress. So there was no effect of principal stress. We have used distortion energy, or distortion energy is von Mises again. Remember, distortion energy criteria, max distortion, von Mises criteria, or there are a lot of names for this. So distortion energy is von Mises criteria. So now this is clear that maximum stress will be on the throat area, this area, this maximum stress will be on this throat area. But to calculate this maximum stress, what we need to calculate? We need to calculate primary shear, just like in bolt. Due to this force, there is one force component here and similarly one force component acting here. So this is primary shear component. Secondary shear component, there is a possibility that due to this force, this joint can be failed due to bending or due to shear. And in this both of these cases, we have the second component will be different. Also, we need to have the strength of parent metal. These and this is are the parent metal. We should have a strength of deposited weld metal, this one, and we should have permissible load. What is the load that is applied? If the load is given, then we can either load is given or either strength is given. Some things will be given and something you will be required to calculate. And what is the maximum load that the deposited metal or strength, in other words, the strength or the applied loads are would be given. And from these values you can calculate anything you like within the for the joints. Now I have just explained you that primary shear is just force divided by number of weld, or divided by area. Force divided by area will give you stresses on each section. And for secondary shear we have two portions, either torsional or bending, or there is also possibility that the secondary shear is a combination of torsion and bending. So for this, initially we need to calculate either number one torsion and second bending, and then in the in the problems you will learn how we combine these two types of bendings, stresses, sorry. For the first type of secondary shear, starting from torsion, what is torsion? Explaining on the white screen. If for let's say that you have this circular rod added here and it is welded on the wall, and you have weld all around the surface. If externally load is applied here, there will be a torsion along the weld. If you see the weld this material is trying to slide on the weld in torsion. So this is torsion stress in the weld. The same metal, the same component, if you apply load in this direction, let's say you are applying load in this direction, due to this joint, if you see here, this joint will try to separate in this direction, or the weld will try to break outside of this surface. This is the surface, and the joint will, the part, this end of the part will try to come out of this joint, so that will be the bending stress. So the secondary shear, due to this load there is a due to this load there is a primary shear, load divided by two simple load, and due to this torsion there is secondary shear in torsion, and due to this load there is a bending, and we have two types of shear, secondary shear, bending and torsion. So starting from torsion, in this case, say this, you have these two types of welds here, and force is applied here. This force causes this part to rotate in this direction, and due to this rotation, this joint is, this part is trying to rotate this joint along the plane, or in the same plane as the joint is available. So the joint will try to rotate in this direction. So this is an example of torsion. This, there, if you take this as a support, there, for this force we will have an equal and opposite reaction, and but reaction on the weld will be in downward direction. So there will be primary shear in downward direction at point O, and there will be a secondary shear or secondary torsion. Will be torsion at point O, this torsion. And what will be the magnitude of this torsion? F multiplied by this distance from this point to this point. uh, Primary shear will be easy. V, in this case V is equal to F, and A is the area of weld. And what is the area? This length multiplied by thickness plus this length multiplied by thickness. So the total area will be this area of one weld multiplied by 2. This thickness is T, which is H divided by H cos theta or H sin theta multiplied by length, or plus H cos theta plus multiply into length. Secondary shear in torsion weld. So for to calculate secondary shear, we initially we have the magnitude of moment. This is moment, magnitude of moment. This, then we have mr by j. This equation, it is similar Tc by j, similar to Tc by j. For this we need to r is the maximum distance or the point of weld which is further away from O, because if m is fixed, in this case m is fixed for complete joint, j will be fixed, that we will calculate later on. This, only this r, the point in the weld which is further away from its centroid, will experience maximum amount of secondary shear. For this we need to calculate j. And what is j? For example, we will study calculation of j for this simple weld. Let's say T1 and T2 are the throat thicknesses of two weld beads. What is throat thickness? It is H 0.707 H1 and it is 0.707 H2. We have height of length of this weld, we have length of this weld. The point G1 is center of this weld, and point G2 is center of this weld. Throat area, what will be the throat area? Area of this weld will be T1 into D, and for this weld it will be T2 into B. So total area of weld will be this, that I have already told you. either you write sine 45, cos 35 or 0.707. Second moment of area for weld 1. For weld 1, this. What is second moment of area? J. What is J? J is Ixx plus Iyy. What is Ixx? BH cube by 12 in x direction, and similarly BH cube by 12 in y direction. Ix, what is x axis? This is x axis. So if you take this an x axis, in this case this is B and this is H. So T1 d cube by 12 is Ix. Similarly, y, what is y axis? Y axis is vertical axis. This is y axis. About this axis, if you take this axis, rotation about this axis, this will become base and this will become height. So d t1 cube by 12. This is j at g1. This is the second polar moment of area at this point. Similarly, for second part as well, we can calculate second moment of area about g2. We have j at g1 and j of material 2 at g2, but we need to shift these two values of j at centroid of overall joint. For that purpose, we need to calculate centroid. This was the total area. Similar to what we have done in case of rivets and bolts, we need to calculate centroid, and for centroid we have this equation: a1x1 plus a2x2 equal to ax bar, where x bar is centroid in x direction. Similarly, a1y1 plus a2y2 divided by a equal to y bar. So by substituting, we have area a1, we have area a2, we have y1. What is y1? Sorry, starting from x1, what is x1? If you take this as O, from this point, what is the distance of centroid of area 1? This will be x1. And what is the distance of centroid of area 2? That is x2. We have area 1 into x1, area 2 into x2 divided by sum of area will give us x bar, and that this x bar will be distance of this g from this or exit in x direction. So this is x bar. Similarly, calculating y bar will be in upward direction, vertical direction. So this is y bar. Joining the 2 points will give us this, and this will give us g. Now we have centroid of this complete weld. From that we can calculate r1 at r2. This is simple trigonometry: x bar minus x1 plus y1 square. Similarly, these two values will give you x bar, y bar. Why only y bar square? Because x1 bar lies on origin. Sorry, y1 bar lies on origin, so only height is y bar. So the second term is 0. So this is a simple equation. You can solve this and you will get r1 r2. Total j of weld. What is j? jg1, j calculated at g1 plus a, like I already explained you, a d square. In this case we have polar distance, we have angular this distance. So a r1 square, jg1 plus ar1 square plus jg2 plus ar2 square. So this equation will bring all the values of j at this. So this is the value of j of complete weld at point G. So this is the polar moment of area calculated. We have calculated all the things. Now there is a possibility that in the question they have given us shear stress and they ask us to calculate weld size. In that case, area will be unknown. So we it is possibility that we need to calculate area, or it is also so what will we do? We will estimate as approximate weld size. What is weld size? Weld size is height of weld. For example, in case of fillet weld, this was h and this was h and this was t. So this weld size, we estimate one value of weld size and then we calculate it and we see if the required answer is achieved. Otherwise we need to check another value of h. uh, up till now you will be wondering that these calculations are very difficult, but just stay with me. I will show you an easy way to calculate all these values. We have the value of jg1 and jg2, and these values are not same as this one. So we what they have done, they have just assumed that as compared to the length of weld, the thickness is negligible. So, and the cube of thickness is further reduced. So the term with t cube can be eliminated. So that will further simplify the equation. So as the t cube terms are eliminated, the equation will be linearized in terms of width. So the equation will become easy. And also setting t1 equal to t2 where the t is linear. For example, in this term t1 dq, they asked to use t1 as unit 1, simply unit value of t. If t is unit, what it changes? If this is unit, it assumes that the welt is a line. It is welt with thickness, negligible thickness or unit thickness, or it is a line. Mathematically, it is very easy. In reality, at the end, after calculation, we have to multiply it with 0.707. But at this point, we can just assume that it is yours. And what it changes, if you change all t1s with 1, the jg1 and jg2, or sum of j which is equal to jg1 at g jg plus jg, shifting 1 plus ar1 square plus jg2 plus ar2 square, shifting all the values to j by assuming t1 and t2 unit and eliminating t cube, t1 cube and t cube value. We change this j to ju. And what is the advantage? It is a dimensionless quantity. This quantity, not dimensionless, not exactly dimensionless, but uh, it does not depend on size of welt, because size of welt, the dependent parameter on size of welt is t. T is 0.707 height of welt. And when we assume this t equal to 1, we eliminated the effect of welt size. And by eliminating the effect of welt size, we have changed this j to ju. And for this ju, this value. From this ju, when we have a value of ju, multiplying it with 0.707 h, where h is welt size and 0.707 h is t, will give us j. So ju is independent of welt size and j is dependent on welt size. And what is the advantage? These values of ju are given in table. You have tables for any type of torsion. For this table is for torsion. For torsional type of weld, for this type of weld, we have value of area, we have position of x bar, position of y bar, and ju. Similarly, for these two vertical line weld, we have area, x bar, y bar, and ju. So for any type of weld that you have, for at your given example, just come to this table 9-1, I think it is. Just let me check what is the number of table there. Yeah, it is 9.1. Just come to table 9.1, check the weld. If the given weld matches with any type of these 6 welds, just get the value of area, value of x bar, y bar, and ju. And if you multiply with ju with any type of, for example, you are assuming that or in the question they have given you that the weld type is, weld size is 10 mm, and it is a square and rectangular weld. Or if it is square weld, in case of square weld, b will become equal to d. So if it is square weld, you know that b is equal to d. So this equation b becomes equal to d. 10 mm weld, so you have value of ju, multiply it with 10 into 0.707 multiplied by ju will give you j for that weld. Similarly, x bar and y bar are exactly at the center, and area is given. So all the values are given. You can just use these value for your problem. So that is an easy way to use all the value. Then we have an example. I will just skip this example for now, and I will go to topic of bending, and then I will end the topic and I will explain you the problem in the next coming week. Now, going into, if the secondary, or if there are three stresses, secondary, first secondary, and this is second secondary stress, secondary shear. If the force is applied in this direction, what it will doing, the weld will try to come out of this plane, so it will fail under bending. If you have weld here and here, or let's say if you have weld here and here, this will be the weld on top and bottom. So primary shear, same as before. What is primary shear? F applied here, F will be acting here, F divided by area of this plus this will give us primary shear stress in the weld. For secondary stress, we have tau double prime, MC by I. What is M? M is bending moment, C is maximum distance from origin, and I is second moment of area. Just like before, you don't need to go into all of detail. We have another table which gives us all the values in case of bending stresses. So it's for the same weld, for example, this I have explained this for shear. So for the same weld, in case of square, B will become equal to D, though the area is given, X bar and Y bar is given, and similarly IU is given. From this IU, just multiplied it 0.707 and size of weld, which is H, and JU will give you J for that specific weld. For example, if H is 5 mm, then J will be different. If H is 10 mm, J will be double. So it is exactly same, just you have to think what is the type of stress the weld is experiencing. The last topic, I have two slides remaining. I wanted to explain the solve problem as well, but I think the slide is already 1 hour. The lecture is already 1 hour long, so I will just finish it here. Uh, in this table, they have given us, there are a lot of electrode types that we can use for weld. So for each type of weld they have given us the value of yield strength of the material and tensile strength. So whatever material you are using for welding, you can just come here and check which is the feasible electrode for that specific welding process. Similarly, if you have, for example, you have the cases, you have, for example, let's say you have butt weld. If there is a tension, axial loading applied on butt weld, then just go to table A20. A20 gives you the value of base metals, yield strength of base metal. Just multiply it with 0.6. It will give you the maximum stress that you can apply. Maximum stress. So what is 1.67? Because we are applying maximum stress of 60%, so 1 divided by 0.6 is 1.67. So we are using 67% of factor of safety, or 1.67 factor of safety. If for the same joint, for the same material, we are applying bearing stress, so you can stress is at up to 90% of its yield strength. If you are applying bending, then you can apply 60 to 66% of its yield strength. If it's simple compression, then again 60%. And if it is shear, as I have already told you that mostly weld fail under shear. So in case of shear, you can apply maximum of 30% of its ultimate strength. Whose ultimate strength? The base material. The ultimate strength of base material, you can apply this value. And also, you will not only apply this value, there we have a plus sign, and it is explained here that for the base metal, okay, but this 30% of ultimate strength, either 0.3 as ultimate or 0.4 as yield, whichever is less. If this value is less, you should apply this value, and if among these, between these two value, whichever is the lesser value, we should apply a maximum of that amount of stress on any weld in shear. So that is the limit that you have to know. This is the last slide. After that, this is the end of lecture. In the last slide, I in the previous slide you know that we have electrode number 60, 70, 80, 90, 100 and 120. So these are the electrode number. These are the maximum amount of stresses that can be applied on each electrode. For it this system, this figure is in inch system. In the book, if you see the book, you have these values in millimeter or MPa. So if your book is also in inches, you can just write, because it is we have open book paper, just write the values here. For example, this is the maximum amount of unit force that you can apply. For example, 12.73 H. This is the maximum amount of force you can apply. And when this H is 1 mm, this is equal to 20.73, because H is 1 mm. When H is 7.8 inch, multiply this term 112.7 with 7.8. So there is no need for this complete table. If your book is, this is only for easy access. So, for example, if you have value of H, just see the value of H. For example, this is the value for example, if this is the weld size, if H is 5 by 16 inch, and the material that you are using is 80 weld material, so maximum stress that can be, maximum load that can be applied is 5.3 kip, or in your book if it is SI units, then it will be written in Newton. So this is the table that gives us the maximum amount of load per unit length that can be applied on the filler material or weld metal. So that is all for the today's lecture, and inshallah in the next week I will explain the problem, I will solve the problem. And there is, I don't think there is any theory left for this chapter. There are only problem left, and those problem I will solve in the next class. Thank you. Allah Hafiz.